PT Multibangun Rekatama Patria is an Indonesian company operating within the geosynthetics industry of civil engineering. Since it was established in 1998, this company has completed hundreds of projects throughout Indonesia. Based on this experience, PT Multibangun Rekatama Patria has become a trusted partner of public and private multinational companies in providing specialist services to their project. PT Multibangun Rekatama Patria has always maintained the quality of materials supplied to projects supported by competent and well-experienced teams. Vision of PT Multibangun Rekatama Patria is to continue as a market leader, maintaining both a competitive and professional image within the Indonesian geosynthetics industry. Mission of PT Multibangun Rekatama Patria has 5 key targets. Conduct company activities to a high standard of ethics and integrity. Increase the awareness of geosynthetic products and their appropriate use, so that customers can choose systems and solutions suitable for their projects. Supply high-quality geosynthetic materials designed by experienced engineers and installed by expert technicians, aimed at providing customer satisfaction. Develop the company with modern and professional resources. Give appreciation to employees by developing their well-being. Creating a safe and convenient working environment for career advancement. Products from PT Multibangun Rekatama Patria: Tensar Stabilization Geogrids, Geogrid Triax. Geogrid Triax has been developed to interlock with aggregate particles in order to create a mechanically stabilized layer within pavements and other traffic areas. Multi-block retaining wall system. Multi-block retaining wall system combines concrete modular blocks with tensor uniaxial geogrids to form a specific type of mechanically stabilized earth structure, namely a modular block retaining wall. Geomembrane. Geomembranes consisting of high-density polyethylene liners are used in many situations where an impermeable barrier is required, especially in extreme environmental conditions. We also provide other geosynthetic products such as geotextiles, drainage materials and composites, as well as geosynthetic clay liners, whichever provides a suitable solution for your project. The warehouse of PT Multibangun Rekatama Patria is only 5 minutes from the Bitung Tangerang toll gate, which provides easy access for material delivery. The warehouse of PT Multibangun Rekatama Patria is located in District Integrated Area Development 2 in Bitung, Tangerang, having an area of 3,300 meters square, which can accommodate the geosynthetic material in an organized and structured arrangement. using equipment operated by professional workers. We verify that the geosynthetic material quality remains intact until it reaches the project site. There is always ready stock, and professional service is our commitment. To share this professional experience, please do not hesitate to contact our team if you need further information. Visit our website at www.multibangunpatria.com.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera bagi kita semua. Perkenalkan, saya Rizky Aprilia yang akan membantu acara webinar kali ini. Kepada Bapak, Ibu, dan rekan-rekan mahasiswa sekalian, saya ucapkan selamat datang di acara MRP Webinar Series yang ke-8 dengan tema 11 Things You Should Know About Reinforced Soil Structure pada pagi hari ini 28 September 2021. Webinar ini dipersembahkan oleh PT Multibangun Rekatama Patria Geosynthetic Specialist. Sebelum memulai acara, perkenankanlah saya membacakan susunan acara webinar kali ini. Pertama, akan dibacakan tata tertib dan tata cara dalam webinar kami. Kedua, sambutan oleh Ibu Mira Magnolia selaku perwakilan dari PT Multibangun Rekatama Patria. Acara kemudian dilanjutkan dengan paparan oleh Bapak Michael Dobi, dilanjutkan dengan sesi tanya jawab. Sebelum mengakhiri acara, kami juga sudah menyiapkan kuis berhadiah uang untuk 3 orang pemenang. Maka dari itu, peserta dimohon tidak langsung meninggalkan webinar setelah paparan berakhir. Informasi terkait sertifikat dan lainnya akan diumumkan di akhir acara. Baiklah, demi kenyamanan bersama, saya akan bacakan terlebih dahulu tata tertib webinar pagi hari ini. Presentasi oleh pembicara akan dibawakan dalam bahasa Inggris. Apabila Anda memiliki pertanyaan untuk pembicara, dapat langsung diketikkan dari sekarang dan selama presentasi berlangsung melalui fitur Q&A yang terletak di bawah layar Anda. Pertanyaan lebih baik jika disampaikan dalam bahasa Inggris. Webinar kali ini juga disiarkan secara langsung di channel YouTube kami, yaitu Multibangun Rekatama Patria di link bit.ly/webinarmrp-live8 atau yang kami share pada kolom chat. Kami tidak menyediakan link absen maupun persensi. Untuk mempersingkat waktu, saya persilakan Ibu Mira Magnolia selaku perwakilan dari PT Multibangun Rekatama Patria untuk memberikan sambutan. Kepada Ibu Mira, dipersilahkan.
Selamat pagi Bapak, Ibu, dan saudara-saudari sekalian. Kami ucapkan terima kasih atas kehadirannya di acara webinar Zoom kali ini. Perkenalkan saya, Mira, mewakili PT Multibangun Rekatama Patria, perusahaan yang sudah berpengalaman dan dalam bidang geosintetik spesialis sejak tahun 1991. Kami berkomitmen penuh dalam mengembangkan kualitas dan juga aktif berpartisipasi dalam membangun negeri sesuai dengan bidang yang kami jalani seperti material geogrid untuk infrastruktur jalan, perkuatan tanah lunak, jalan akses pelabuhan, pembangunan terminal peti kemas, perkuatan timunan, dan penanganan longsor. Ada juga material geomembran untuk pembuatan kolam penampungan limbah atau air bersih, dan juga untuk landfill atau TPA. Kami berencana untuk secara rutin berbagi pengalaman yang berkaitan dengan bidang geosintetik dan juga geoteknik melalui webinar Zoom ini. Sharing webinar ini kami adakan sebagai bentuk kontribusi kami di dunia teknik sipil secara umum maupun bidang geoteknik secara khususnya. Semoga webinar ini bisa memberikan manfaat positif untuk kita semua. Sebagai penutup, kita bersyukur Jabodetabek sudah berada di zona orange COVID-19. Tetapi kita tetap harus mematuhi protokol kesehatan 5M, yaitu memakai masker, mencuci tangan, menjaga jarak, menjauhi kerumunan, dan membatasi mobilitas. Selamat mengikuti webinar ini. Terima kasih.
Terima kasih kepada Ibu Mira atas sambutannya. Selanjutnya, webinar hari ini yang bertemakan 11 Things You Should Know About Reinforced Soil Structure akan dibawakan oleh Bapak Michael Doby yang merupakan Regional Manager Asia Pasifik of Tensar. Sebelum beralih ke Bapak Michael Doby, saya akan membacakan CV beliau. Bapak Michael Doby telah menempuh kualifikasi akademiknya pada tahun 1973 di University of Bristol dengan gelar sarjana Bachelor of Science in Civil Engineering dan melanjutkan di Imperial College London pada tahun 1977 dan berhasil meraih gelar Master of Science in Soil Mechanics under Professor Bishop. Beliau mendapatkan gelar Professional Charter Engineering di UK pada tahun 1978 dan merupakan seorang fellow ICE di tahun 2011. Beliau juga mendapatkan Charter Institution of Highway and Transportation pada tahun 1992. Bapak Michael Doby memiliki pengalaman lebih dari 40 tahun di bidang geotechnical engineering di Inggris di luar negeri, terutama yang berhubungan dengan jalan raya, perumahan, jembatan, dan dermaga. Baiklah, sekali lagi saya ingatkan kepada Bapak dan Ibu yang memiliki pertanyaan untuk Bapak Michael Doby, bisa langsung menggunakan fitur Q&A yang terletak di bawah layar Anda. Pertanyaan dapat disampaikan dalam bahasa Indonesia, namun akan lebih baik dalam bahasa Inggris. Tanpa memperpanjang waktu, kepada Bapak Michael Doby, the time is yours. Silahkan, Pak.
Good morning, everybody. First of all, thank you very much to Kiki and Mira for their very nice introduction. And as usual, I would also like to thank very much all my colleagues in PT Multibangun Rekatama Patria who organize these events. I'm amazed to see we've now reached number 8 in this series, but it's been a great pleasure to do them with this incredible team to help. So thanks very, very much. Today, I'm switching from purely geotechnical topics to something related to reinforced soil, which is an area I've worked in for many years. So let's just introduce what we're going to talk about today. So yes, it's the 8th in this series of webinars on geotechnical engineering, looking at reinforced soil structures. And I'm going to talk about 11 items. I'll just come back to that in a second. The 9th of these webinars will be held next month, where I'm going to look at a particular technique using reinforced soil, which is to do with load-bearing bridge abutments. They are very, if you like, high-level structures to design, and I think it's very interesting to look at what can be done with these techniques. But that's next month. Here is an outline of the webinars that we've been holding during this year, and as you can see, we're now in September. And we will continue through to the end of the year and then bring the series to an end. So let's look at some pictures of reinforced soil structures. I'm assuming that most people listening in today have some experience or knowledge about this form of structure, but this is a very nice retaining wall holding up the railway that heads off to the Jakarta International Airport. Something a bit different here. This is actually carrying skiers in a ski field in Australia. Here's a wall supporting the Parliament building in Brunei. This is a slope. It's a vegetated structure, but it's also a retaining structure. One of the very early ones built here, that was built over 30 years ago, still serving very nicely in Hong Kong. And this very elegant approach structure to a bridge in the Philippines. And then one last picture. This is actually a load-bearing bridge abutment. That's the sort of structure I want to talk about in the next webinar. So why did I choose this title? And Well, it's because I find in working in this field for such a long time now that I think there are a few misunderstandings and confusions about some aspects of reinforced soil. And really, I've picked out 11 things. You might say, why 11? Well, 11 is quite a nice number. It gives me about 5 minutes on each topic, which means I need to get a move on because I know how many slides I have to present to you today. But I could easily have 11 more. There are many topics that I think require discussion in this particular field, but let's see how we get on with these topics today. As I go along, as usual, these little blue boxes will appear from time to time to make a special point or to maybe ask a question or two. May even be related to the quiz at the end of the webinar. The material is aimed really at civil engineers who have some involvement in the planning, design, or supervision of reinforced soil structures. Or I hope also the information could be of interest to more experienced, either geotechnical engineers or geosynthetics specialists. I use I use 3 main abbreviations to save writing it out all the time when I make the slides. So these 3 get used quite a lot. RSS, reinforced soil structure, that's the term I'm using there. RSW, reinforced soil wall or retaining wall. And RSB, the reinforced soil block, that's the block of soil that's actually reinforced by the geosynthetic material. So I could list to you right now the 11 items, but I thought rather than that, let's just bring them on one by one. So we'll start off with something about principles of reinforced soil. And this particular little isometric sketch, I've been using it for years, but it shows the main elements of a reinforced soil structure very nicely. Of course, the main part of it is a fill, a soil. Then we have layers of, in this case, geogrid reinforcement buried in the fill, and some sort of facing. And one nice thing about using polymer geogrids is that we can use quite a wide variety of fill types. Likewise, we can use many forms of facing. And in this webinar, I'm talking about the use of polymer reinforcement. The word geogrid and reinforcement is really interchangeable, and I sometimes use either of those 2 terms. Here's a nice picture of a wall built a few years ago in the UAE. 18 meters high, is quite big. And you can see that the toe has been protected by some riprap because this is a stream bed. And you can see the width of the stream here in another view on the same project, quite a big stream bed. And here we can see water actually flowing in the stream. And you can see this is the Middle East, where it doesn't rain very often, but when it does rain, it's very heavy. And you can see that rapidly this dry stream bed has turned into a major water flow. Here it is further down the wall. And in fact, what we're going to look at now, just down here, somewhere where that red circle is, we're going to look at that section because when the flow had stopped and people looked carefully down here, they found that part of the facing of the structure was missing. And what had happened was that the very heavy or the very strong water flows in the channel had actually scoured away the material underneath the facing, and it had basically dropped downwards. And there's a view from the front. You can see very clearly what's happened. Those are the modular blocks. But what is very impressive about that view is that although the facing is now missing in that section, the block of reinforced soil has remained perfectly stable. So let's just go back to the beginning again. There's the initial picture. You can now see what happened. They had unfortunately forgotten to put the riprap over this section. But if we think about a cross section here, what do we have? We have soil and layers of geogrid, designed obviously to meet certain requirements. And on the front, we have a modular block facing. So let's just take away the background and just look at the cross section. So the important point here is that the RSB, the reinforced soil block, is the structure. And it's a composite consisting of soil and geogrid or geosynthetic reinforcement. And the facing is there essentially to make it look nice, to prevent erosion of the soil at the facing, and also to provide some local stability at the face. Unfortunately, what happened in this case was that there was erosion down at the bottom and the blocks dropped down. But what was very interesting is that despite this happening, the highway remained in service and the crash barrier remained intact. And we can see it here in this picture along the top. So this is after the facing fell away. And you can see there's no sign of any damage even to the crash barrier. So this makes a very nice important point about reinforced soil being this composite. What do? Well, they repaired it. They put the facing blocks back until it was completed. And this time they remembered to add the riprap to protect the toe from water flows. So I think this is a very nice demonstration of how reinforced soil works as a composite, and also that it can withstand some pretty serious situations and recover very nicely. While we're on this section, one more little point I want to make, because I often see this appearing, and that is if you have a structure like this, do not pile the facing by itself, because I often see this on drawings, that people have a structure like this, and they put a row of piles. Sometimes it's little wooden piles here, we call them cheruchuk, but we often see that just underneath the facing. It's not a good idea. If you do need to improve the foundation conditions, then this should be done by treating the entire reinforced soil block width. So just a few more words about this reinforcement soil composite, because there's some work done here in Japan many years ago. It was a trial wall. It's reported by Tajiri et al. Back in 1996 in one of the Kyushu conferences. And there's a simple cross section. And you can see 6 meters high, geogrid's 3.5 meters long, and roughly 1 meter spacing, but there are some little secondary bits to make sure you don't get a local failure at the facing. And you can see there the main properties of the fill and the reinforcement. Now, many trial walls were built like this years ago because people were trying to learn about the technique. But what was particularly interesting in this case is that the researchers arranged to cut the reinforcement inside the soil. They did this by using electric wires that were embedded in the fill, and you could make them hot. And when you made them hot, that would melt through and cut through the geogrid. So they gradually reduced the length of the reinforcement. This is really the most incredible piece of work. Anyhow, there's the first series of cuts. Each cut is removing roughly 30 centimeters of the geogrid. And then there's the second series of cuts. So in the cross sections now, brown is intact and green has been cut into short pieces, roughly 30 centimeters in length. The next series, you can see how they're shortening the geogrid. And incredibly, they go all the way to this situation, and they reach cut number 60, and then the wall fails. Quite an extraordinary piece of work. So what are we going to learn from this? So if I now go into a stability program, this is a slope stability program, and I put in the initial geometry of that structure. There it is. You can see the spacings of the geogrid and everything connected to the facing. Sorry, I've drawn it the other way around, but I'm sure you can realize that. And I can use a very nice non-circular analysis technique to investigate stability, which I'm going to explain a bit more detail later on, but I'll just do it quickly now. So what we're going to do, we put some random non-circular surfaces there, and we use a special technique to find the critical surface, which is basically the pink colored surface you can see there. It's a two-part wedge, and that is the critical one. And we find when we've done that the safety factor just over 1.3. So what we'd normally be aiming for in a structure like this. That's okay. But if I now go to this situation and I do the same analysis, that was the situation when they'd reached cut number 60. Of course, if I try the same technique, I get very low safety factor. The structure is predicted to collapse. And of course it did at that stage, but just prior to that, it was perfectly stable. So there's something else going on in reinforced soil. There's an additional composite behavior which we're not really taking into account. Well, luckily, a colleague of mine, Dr. Andrew Lees, he published this paper. I helped a little bit, so my name's on there, but Andrew did most of the difficult work. But he looked at this particular situation of the potential benefit, because what's so clever about this experiment is that the reinforcement effect is being reduced, but the effect of the geogrid apertures confining and stabilizing the fill is left behind. And that's what I call the composite effect. So Andrew Lees is due to speak to us in an ENA IGS webinar in December, and I'm very much hoping he'll be talking a little bit more about this particular situation. Number 3, walls versus slopes, reinforced, of course. Is there a difference? Let's have a look at that. There are differences from a kind of a general point of view. So generally slopes are defined with facing angle less than 70 degrees to the horizontal, and normally they have a soft or vegetated facing. And in fact, there are not very many published design guides for reinforced soil slopes. When it comes to walls, they're normally steeper than 70 degrees, normally with a concrete or a hard facing, and there are many published design guides for this form of structure around the world. But let me show you something to give us a bit of a feeling about what happens as a structure becomes steeper. So I've drawn a picture here of a block of soil, and we'll assume it's stable at a certain angle. And what I want to do now is to add another thin wedge of soil with a top width of 0.1 of the height. And therefore it gives us the facing angle. And from that, we can calculate the weight of that slice. And then we put in the resisting forces from the soil, which of course is a normal force and a shear force. And we do some calculations. I'm going to use a phi of 30 degrees. We can calculate the weight of the thin slice. And we can draw a force diagram because we know the weight of the slice. We know the direction of the normal force N. And because of the phi value, that limits the value of S. And of course, what's happening here is that we cannot complete the force diagram. So of course, as we know, the wedge simply slides off. We know it fails. But what I can do from this, I can form a relationship by plotting this shear resistance in terms of the weight of the slice as the facing angle increases. And the diagram looks like this. So facing angle along the horizontal axis and the shear resistance on the vertical one. And as the facing becomes steeper, the resistance from the soil is reducing simply because you're tipping it up more and more steeply. So it's failing. But what we can do to prevent the failure is to add force from reinforcement. We call it T. And I can now do the same thing again. I can do some calculations. I can draw a force diagram. But now, because of T being present, I can complete the force diagram and I can get a stable situation. It looks like that. And I can therefore now calculate S over W as the facing angle increases again. So we'll go back to this graph and we get the blue line. So the blue line is the resistance from the soil when the reinforcement is added. And therefore the difference between the two is the additional soil resistance generated due to the presence of the reinforcement. Now what you can see is as the structure becomes steeper, the generation of additional shear resistance from the reinforcement is getting higher and higher. Of course, that's one of the clever benefits of reinforced soil. We're using the failure of the soil to kind of stabilize itself. That's why it works so well. I can also draw a diagram of the required tensile force in relation to the weight of the wedge or slice. And you can see that the required force from the reinforcement increases very rapidly as the facing angle becomes steeper and becomes very high as we approach 90 degrees, which of course would be a vertical retaining wall. So we can see this also in design charts. These are the slope design charts, which were published by Schmertmann many years ago. And one of the charts gives you a thing called the force coefficient on the vertical axis against the slope angle on the horizontal axis. And you can see how the force requirement is increasing as slope angle becomes higher. So for example, if we compare 45 degrees and 78 degrees facing angle, then we get a much greater requirement for reinforcement. So is there a difference? Well, the first difference is there's a very different contribution to the internal stability from the reinforcement. It's much greater in retaining walls than slopes. And there is a difference in terms of design methods. Design methods for walls and slopes tend to be different, although if you're going to analyze using something like limiting equilibrium or FEA, then you can apply those methods in exactly the same way to walls and slopes. In fact, I did tackle this topic in a paper published in an UNPAR event, the Slope 2019 in Bali. This paper here, if you're interested, we can certainly let you have a copy. But that looks at this whole issue of retaining wall design compared to reinforced soil slope design. Number 4, effective stress design. This is something that is one of the most important things to get right. And what do I mean by that? Well, when we are designing a reinforced soil structure, and here's a typical cross-section, 3 zones of material, a reinforced fill, a backfill, and a foundation. And I've referred to them as S1, S2, and S3. Then which strength parameters do we use? Because we need for the soil layers unit weight and shear strength. And also, of course, if water is present, we need to take into account water pressure. So what do? Well, we go to site, we get a nice big sample of fill, and then we carry out all sorts of index property testing to find out what the soil consists of. We maybe classify it. And then we normally do a compaction test to find out information about the optimum water content and maximum dry density. And then having done that, we can prepare samples to carry out shear strength tests. But here's one of these blue reminders. The shear strength tests must be appropriate for the design requirements. Now, what do I mean by that? Well, there are 2 principal definitions of soil shear strength which we use. The first is what we call drained or effective stress, where the important parameters are C dashed and phi dashed. And the dashed is important because the dashed indicates that we have strengths in terms of effective stress. Then we have an alternative one, which is undrained shear strength, where we simply say the strength equals the undrained shear strength. And these are 2 definitions which we use in geotechnical engineering. And if we draw have a little table of our 3 soil zones, S1, S2, S3, well, S1 and S2 are generally fills, almost always fills, but S3 could be a natural foundation soil. But the point is, for the fills, then for all soil types, coarse, fine, clay, whatever it is, then we use the drained or effective stress parameters C dash and phi dashed. It's slightly different in the foundation, but that's not the topic today. We're just thinking really about the fills. We would never use undrained shear strength in the fill soils. In fact, why do I put C dashed in brackets? Well, most published codes and standards recommend that you would use C dashed is 0 or a very low value for reinforced soil design. Now, here's a slight problem, because when we look at available strength tests that you might use to determine these properties, then we are rather limited, especially for fine soils. So if we're talking about fine soils, and we're often using fine fills here in Indonesia and many other parts of Southeast Asia, then we basically have a choice of triaxial CU or CD tests or slow shear box testing. And the slight problem is that effective stress tests on fine soils tend to be expensive, and this can lead to difficulties. Now, in the earlier webinars, in particular MRPs 1, 2, and 3, I went into some detail about soil properties, index properties, also using the shear box and also the triaxial test. So if you want to know more about that, I'd suggest we can recommend that you look back at those. I think they're easily available if you'd like to review those, both as a video, and also there are PDF versions of all of those webinars. So there we are, extensive information in those earlier ones. So let's just remind ourselves about what an effective stress test looks like, in this case on a fine sand. So we have, in this case, from a shear box, shear stress versus horizontal displacement. And then also very useful to know the vertical displacement of the shear box versus the horizontal displacement, which I plot underneath it. And then from the upper diagram, and knowing the normal stresses, we can derive the phi values by plotting shear stress against normal stress. This is all very basic stuff and discussed in great detail in the second webinar. And then I've got a little table down here with some important information. And in fact, that information in that box really is plus the diagrams. This is the minimum information you require to make an assessment of a shear box test. And this test is very adequate to give you C dash and phi dashed for a sand like this. And one of the really important things to notice here, it's a fast shear test, and the rate of shearing was 0.8 of a millimeter per minute, perfectly acceptable for a sand. If I now switch this picture to a fine soil, so this is a similar test on a fine sandy clay, also a picture we looked at back in one of those early webinars, then we can get very nice results in terms of effective stress, in other words, C dash and phi dash for a fine soil, but the test has to be a consolidated slow shear box test. So if we now look in the tabulation down below, we see a rate of shearing of just 0.0072 millimeters per minute. So it's very, very slow. So if you want to get suitable results from this kind of testing in terms of effective stress, then you need to test slowly. I made this point also back in the second webinar that the Indonesian standard which covers this test method appears to have a slight error in the way you calculate the rate of shearing. Basically, it's 50 times too fast. Now, having talked about the importance of using effective stress and how we might measure it, I'm now going to come to a special topic, which I give a special title to. I did mention this actually in one of the earlier webinars as well, but I call it the high C, low phi problem in fine soils because I see it frequently. So what do I mean by that? Well, let's take a table of some data here. This is from a site investigation report in Indonesia many years ago that I received. And you can see all the nice information here, various index properties. You can see if you look down the column on the left-hand side with values, and all the standards are mentioned there, Atterberg limits, a summary of particle size. And then at the very bottom, we have direct shear tests. Now that particular SNI standard there is for an unconsolidated fast shear test. So the values you see there of C and phi, these are what I call high C, low phi results. And if you want to look at an actual test result like this, so here is a fairly fine soil. It's an A27 soil, low plasticity soil. It's a desert soil in this case, but this is a fast shear box test. And how do we know that? Because if we look at the table of data there, we can see the rate of shearing was 0.8 millimeters per minute on a fine soil. So what do we get? We get this kind of behavior, high C, low phi. Now, if you're presented with that data to design a reinforced soil structure, you shouldn't use it. You need to make some kind of reassessment and try to decide what would be a suitable C dash and phi dash to use, maybe based on index testing. What's going on? Well, here's another picture of a shear box. It's just a shear stress, normal stress result. And this is a fast shear box test on clay. And you can see we get this very flat line. So we've got the high C, low phi. Why is that happening? Well, the problem is that the three normal stresses there, the sigma n values of 40, 120, and 200, they are total stresses. They're not effective stresses. We don't know what the effective stress is during the test because we cannot measure the pore pressure simply in a shear box. So that's the problem. So that's why we cannot use that kind of result to design a reinforced soil structure. We need to have results like this. In this case, maybe carried out by a slow shear box test. And that would be a typical result there for a fine soil. So why is there a difference? Well, the difference is that the distances between those data points are the pore pressures. So at the high stresses, we get positive pore pressure, and the low stresses, we get negative pore pressures. And because of that, it turns the envelope and gives us the red one, whereas what we really want to have is the blue one. And that would give us the right kind of properties. So sometimes I talk about this and it remains difficult to convince people. So to help convince people, I'm going to show you the results of designing a reinforced soil structure for two sets of strength data. They're the two you see there. So we're going to use C' of 2 kilopascals and phi' of 27 degrees, very typical for a fine soil. And then we're going to use the C of 30 and phi of 10 degrees. I purposely leave off the dash because those are not effective stress strengths. And we'll look at the difference or the effect of those two sets of strength property has on the design. So here's the problem. A 12-meter high structure, 85 degrees. And the first problem is to find the highest possible unreinforced soil slope with a safety factor of 1.3 for the two soil strength values given there, the 1 and the 2, which I mentioned earlier on. So what you would do, you put that into a slope stability program, and you basically move the circles further and further down the facing until you start to get a safety factor less than 1.3. So what are those heights? Well, for the C' and phi' values, it's just 0.5 of a meter, and then you start to get failures. But for C of 30 and phi of 10, even a 6-meter height it still has an adequate safety factor without any assistance from reinforcement. So we already see a bit of a problem there. What's problem number 2? So problem number 2 is to take the same situation and to find a layout of reinforcement with the safety factor as close as possible to 1.3 everywhere throughout the slope. It takes a lot of time to do that, but not too difficult. With a nice piece of software, you can do that. So let's look at the results. So I've done this in a program called Tensar Slope, and you can see there the layout of reinforcement. I hope you can make it out there, the red lines, the 8-meter height of the structure. And in this particular case, we have, actually, sorry, it's 12, bigger, it's 12 meters high, it's 12 meters high. So we have a very nice layout of reinforcement, and you can see what we have is a closer spacing at the bottom and the spacing becoming slightly wider at the top with a gap of a ½ a meter at the very top, because that was the maximum height without reinforcement. We found that earlier on. So this is what we expect to see. Typical layout of reinforcement to reinforce or stabilize the structure of that height. So we're happy with that, but that's for C' of 2 and phi' of 27 degrees. If I switch, oh, sorry, the safety factor down there, just over 1.3 everywhere. If I now switch to C of 30 and phi of 10, then this is the required layout of reinforcement. First of all, we have the huge 6-meter gap at the top because that doesn't require any reinforcement. But then we get a very dense packing of the reinforcement towards the bottom. It's not what we expect. Yet that's what you'll get if you use the high C, low phi to design a reinforced soil structure. It's clearly incorrect. No one would want to accept that as the design, but that's what you get from those properties. Safety factor still just over 1.3. Same number of layers of geogrid. So the main reason, just to remind you one more time, why do we get the high C, low phi? Generally because people are measuring strength in fast shear box tests because they're cheaper. That's the normal reason. Unfortunately, the slow shear box test could take a week or so to carry out. Clearly, it's more expensive. There is a lot more information about clay fills in general in the 4th webinar. Again, you can see that or get hold of the PDF of these slides if you wish to. And that covers topics like pore pressures in clay fills and the importance of certain drainage measures that should be taken when you consider using fine fills. Number 6. Number 6 is something which is very basic to reinforced soil. It's all about interaction. Interaction between fill and reinforcement. So here's a nice photograph which I've used for many years to show people how nicely geogrids can embed themselves in soil. So you get a very good interaction between the two materials. And there are two kinds of interaction we want to understand: sliding and pull out. So how do we measure this? Well, to get sliding interaction information, we carry out a large shear box test, and we adapt the shear box so that we can fix a piece of GeoGrid in the bottom half like that. Then we put the shear box together, and we fill up the top half with some fill as well, and we carry out the shear box test. So what we'll have is a cross-section something like this, so that when we do the shearing, we're pushing the top half, which is soil, over the bottom half, which is soil and GeoGrid. So we get an indication of the effect of the GeoGrid on the sliding resistance. And of course, we normally do the same test without the GeoGrid to get a base value for the soil by itself. So that's the sliding interaction test. Pull out, generally more complex because you need normally a bigger piece of equipment, something like this, where you bury the GeoGrid in a box, fill it up, apply a load, and then you go out to the front of it and pull on it to do the pull out test. To be honest, these are normally more of a research level test. And this would be a typical section. So you can see how I've shown here the normal stress being applied by an airbag, which is another way of doing it, where you pressurize the airbag. And what you do, you're pulling towards the left, and you have the GeoGrid buried down there. Now, I'm talking in this case about GeoGrids which have fairly thick transverse members on them. And what we normally do then is we attach transducers to those to measure the movement of each individual part of the GeoGrid. And the kind of result we get from that would be something like this. Now, this graph shows the load being measured at the clamp versus the displacement. And then the different colored lines represent different points along the GeoGrid. So the red line would be the clamp itself. And then we get bars 1, 2, 3, and 4 going all the way back to the buried end of the GeoGrid. And clearly at the far end of the GeoGrid, the displacement is much smaller because as you load the GeoGrid by itself becomes longer. It extends. So this actually makes pull-out testing quite complicated and sometimes quite difficult to interpret. But that's what a typical result can look like, especially when the pull-out is incomplete. For pull-out tests to work well, you need to have quite short pieces of GeoGrid, especially if the normal stress is high. Otherwise, you simply can't pull the material out. Anyhow, I thought I would show you, one important point here. So let me just go to this blue point, is that when we do interaction testing, whether it's pull-out or sliding, it needs to be an effective stress test. It needs to be a drain test. If you remember the discussion earlier on about effective stress design. Now that's easy for coarse soils, for gravels and sands, no problem at all. But it's very difficult for fine soils. It's my experience that in the literature, there are very few published results of genuine effective stress interaction tests. Simply because if you have a large shear box and you put a clay fill into it, it takes a very, very long time to shear if you want to make sure it's an effective stress result. Now, let me just show you how the different kinds of shear interaction relate to each other. So I'm going to show you some results from doing interaction testing, in this case with a medium to coarse sand and gravel, with 3 grades of GeoGrid. And there are 3 different kinds of tests going on. The soil-to-soil sliding, which would look something like this section here. So we have a 50 kilopascal surcharge on the top, and we simply push the soil in the top part across the soil in the bottom part to get the soil shear strength. So that's a typical soil shear box test. We then do the one with the GeoGrid in it, which looks like this. So now it's same basic test, except now we have the piece of GeoGrid clamped at the midpoint to give us the effect of sliding over GeoGrid rather than sliding over soil, or sliding over GeoGrid and soil. And those are both carried out 1 millimeter per minute because it's a coarse soil. And then finally, we have the soil to GeoGrid shear generated by the pull-out test. Now, this is a slightly different situation because you have shear going on both sides of the GeoGrid. But I'm just going to show you a comparison of the shear resistance or shear stress generated on one side only in each case. So we look at that in the graphs that follow. And in this case, for all 7 tests, that's 1 soil test, 3 sliding interaction, and 3 pull-out tests. The one thing that's the same is that we have a 50 kilopascal normal stress. That's about 2.5 meters below the top of a structure. So here is, I'm just showing the shear stress versus displacement diagram, but here is the basic shear box test on the soil where you see the peak value dropping down to the constant volume value. But we normally expect that in a well-compacted soil. We then add to that diagram the sliding interaction tests. And you can see that they don't quite get that sharp peak, but after some displacement, they end up at shear stresses slightly less than the soil by itself, which is what we'd expect, and that gives us the interaction factor. But when it comes to pull out, again, just looking at the shear, oh, just to remind us that we have 3 grades of geogrid. You can see them there in the legend, a 520, 560, and 580. Basically, the 520 is the thinnest and 580 is the thickest. So when we look at the pull-out test, looks like this. We're looking at the shear on one side only, and we get those lines. Now, the reason why we go to much bigger displacements is that the displacement is measured at the clamp. Think back to the earlier diagram I showed you. But what's interesting here is that the thickness of the geogrid, in this case, is having a very big effect on the generated pull-out resistance. And that's not surprising. Let's have a bit of a think about that, because we can see from that testing that when it came to direct sliding, there was a slight drop-off in resistance due to sliding over the geogrid and soil combined. But when it came to pull-out, this was significantly affected by the thickness of those transverse bars I mentioned earlier on, because they create a greater anchorage as they become thicker. Now, here's a very nice picture. This was made many, many years ago. Just think of it like a kind of X-ray picture of a piece of geogrid being pulled through soil, where the whitish color is compression being generated in front of the transverse bars, which are here, the white blobs. And basically, you can probably guess from this, as those white blobs become fatter, they're going to generate more pull-out resistance. And that's what we saw in that previous result. So that was a few words about interaction testing and what we have to do to learn about it. But what about the relative importance of sliding versus pull-out? Well, just a few slides on this, but this is something where I see a lot of confusion. I see a lot of effort being placed maybe in the wrong direction when it comes to doing this testing. But let's have some words first, and then we'll demonstrate this. So here is a typical cross-section through a reinforced soil structure with a sliding mechanism there, sliding over geogrid. Now, the point is, if you have a sliding mechanism over geogrid, then the sliding interaction factor affects the entire length of the geogrid and clearly has a major influence on the design. That's really important. Now, if we switch this little diagram to looking at pull-out, something like this, so we're looking at the pull-out at the second grid from the bottom there, then pull-out has a very minor influence on the design because the length of geogrid, which is actually involved in the pull-out resistance, is very short, especially at the bottom of a tall structure. Maybe the top geogrid or the top 2 geogrids may be slightly critical, but towards the base of a structure, pull-out is of little consequence and not important at all. I'm talking here, of course, about geogrids, though. I'm talking about materials which are continuous in their extent in all directions, rather than strips or straps. I'm talking about geogrids, and this is the kind of message I would like to get across. But how can we demonstrate this? So I'm now going to go to a piece of software called Tensar Soil, which we can use to design reinforced soil structures. And I've set up here an 8-meter high retaining wall with a surcharge on it. I've chosen reasonably moderate quality fill, and I found myself a stable layout there using one of the US tie-back wedge design methods. And this design is fine, it's good. Now, to make this design, I set all of the interaction factors to a value of 1. That's sliding on the geogrid, sliding on the base, all of those And there's a piece of geogrid at the bottom of the structure, so you get sliding on the geogrid at the base of the structure as well. So I'm now going to go into my interaction factor input window, and I'm going to go to the pull-out one that's just there inside the red circle, and I'm going to change it. I'm going to halve it to 0.5. So that means that when you have a pull-out interaction, we only take half of the soil shear strength rather than the full shear strength. And we set that. And when that happens, you can see in the little diagram in the middle of the screen now, we see there we have a sign that says PO. It's a pull-out failure. The top geogrid has a slight problem in pull-out. Well, we can fix that very easily. So what do? We go into this design method, and we're going to make the top geogrid 1 meter longer. We go okay, and you can just see it there, and that fixes the problem. So if you do have a slight pull-out problem, it'll be at the top, and you can easily fix it by doing something like that, depending on the design method. Now, let's do the same thing now with the sliding interaction. So we go back into this window, and I'm going to change the sliding interaction coefficients to 0.5. So what does that mean? It means that when you have a sliding interaction, you take half of the soil shear strength rather than the full soil shear strength on that sliding plane. And if we do that, and we analyze, we get all sorts of no's. You can see there sliding external stability and sliding internal stability. You see the yellowish and red no, because it's not adequate. And if you look on the cross-sectional diagram, you can see lots of sort of fat red lines indicating sliding over those layers of geogrid. How do you fix the problem? You simply have to make the geogrid longer. There's no other way to do it. So currently the length of the base of the structure is 5.6 meters. And by a little bit of trial and error, we find out we need to make that 8.2 meters to get rid of all of those sliding failure messages. It's a huge, huge effect. So by way of summary, in the case I showed you, it won't always be identical every time you do it, but it'll be similar. So reducing the pull-out interaction factor from 1 to 0.5 required a 1 meter lengthening of the top geogrid. Whereas reducing the sliding interaction factor from 1 to 0.5 required that geogrid length was increased from 5.6 meters to 8.2, which is almost a 50% increase in cost of the geogrid reinforcement in that case. So it has a major effect. I make this point because people are remarkably interested in pull-out resistance, and you get all sorts of research into it, and you get a lot of papers published about it. You get far fewer papers published about sliding interaction, yet that is actually the important one. And luckily, it's the easier one to do because those 30 centimeter shear boxes, they can be found here and there, but a pull-out apparatus is quite rare. Now we're on to number 8, and I think time is looking quite good. And I want to move now to a different but very, very important topic, which is all about durability and degradation of polymer reinforcement, and a few words about that. If I look to European practice, then there is a European standard, 13251, which tells you about the requirements for using geosynthetics as reinforcement in things like retaining walls and so forth. And then there is a very good supplementary document, the technical report 20432, which gives a lot of detailed information and guidelines about determining long-term strength of geosynthetics for soil reinforcement. If you want to see similar information in US practice, there is an AASHTO R69. I see from the internet the latest version is just last year, 2020. I don't have that version of it. I think I have an older one. But it gives you similar kinds of advice about how you should approach determining the long-term strength of geogrid, taking into account various things that can affect it. And that's what I want to look at. Before I get there, I just want to talk about these modes of degradation. Now, these are diagrams coming from that technical report I mentioned, where they designate forms or degradation procedures as in 3 modes. Mode 1 is where if we look at a residual property, which for example could be the tensile strength versus time, it drops very quickly at the beginning and then it doesn't change very much after that. Obviously, installation damage would be like that. And then mode 2 is a gradual reduction throughout the lifetime of the structure. That would be some chemical effects. In this case, you can determine a reduction factor based on time, and you can put that into your assessment of GeoGrid long-term strength. And then there is mode 3, in which nothing much happens until you get almost to the end of the design life, and then there's a sudden reduction in strength. In this case, a reduction factor in the normal way doesn't make much sense, but what we have to do is restrict service life to make sure we don't reach that sudden downturn in that particular degradation. So those are very useful concepts. So what I want to talk about in the next few minutes are some of the typical durability problems that we investigate. The four main things are weathering, which is UV, exposure, in other words, to the atmosphere, and then microbiological degradation, oxidation, and the effect of liquids, principally acids and alkalis, and others on strength of polymers. I'm going to concentrate on oxidation. I don't have time to cover everything. These are investigated in two ways. We have what are called screening tests, which are relatively quick, and they're generally used in approvals, and also we have lifetime prediction tests. Now, the lifetime prediction test is similar to a screening test in some ways, but generally carried out over longer time periods, a bigger range, perhaps of temperatures, or however it's being done, and they're going to take longer, basically. But they are vital if you want to predict reduction factors for typical reinforced soil structure lifetime, of say 100 years or so. Here is a list of the European standard screening tests. You can see there those four main degradation procedures: weathering, microbiological, oxidation, and resistance to liquids, acids and alkalis. And those are their titles. We don't need to read those today, but just a brief mention here. These are the targets you're trying to reach in each of those ones. I'd have to say, on the whole, they are not particularly onerous. If we look at oxidation there, after 112 days at 10 degrees centigrade, you need to retain 50% strength. Well, 50% is half. That's not a very wonderful target for a typical polymer reinforcement, even under those conditions. Let's just also understand a little bit about screening tests, because this European standard 13251 is all, I mentioned it earlier on, and it has an Annex B, and I'm afraid there are lots, I don't like lots of words on slides, but I got quite a few words here. But I just want to make one point that's mentioned in this standard, talking about these screening tests. You can see two of them mentioned there. It says, the tests described in this annex do not allow for the determination of reduction factors and are screening tests to show the ability of a product to serve for a certain time. So these cannot really be used for long-term determination of the life of a geosynthetic reinforcement material. Let's go briefly back to oxidation and talk about that for a couple of minutes. And I'm going to show you one way of examining oxidation. Oxidation is one of the problems for the polyolefins like HDPE and polypropylene, and therefore we have to look at it very carefully. But in this case, we're going to look at testing using what's called an autoclave, which is some kind of cylinder where you put the material inside there and you apply, in this case, high temperature and high pressure, and you take out specimens from time to time and test them to see what's happening to their strength. And here's a typical result. So you see residual strength on the vertical axis versus the time of exposure inside the autoclave on the horizontal axis. And you can see that mode 3 behavior very clearly. So up to about, 220 days, no loss of strength, but then it suddenly drops off. That's at 60 degrees centigrade and 51 bars. The green data is for 70 and the red data is for 80 degrees. And from interpretation of this, which is a fairly specialist thing, then we don't come up with reduction factors, we come up with design life. And you can see there, even at 30 centigrade for this particular material, is pretty high, almost 250 years predicted design life in terms of oxidation. So if we're looking at durability of either mode 2 or mode 3, then this type of lifetime prediction testing is required to be confident about the long-term behavior of the material. Durability screening tests by themselves are not sufficient. Now, another point I'd like to make here is one, you might say, what does this mean? Creep of polymer reinforcement is not degradation. It's because I see this being mentioned quite often, and I think it's it needs some explanation. So here are some, in this case, HDPE geogrids laid out on the site behind a retaining wall facing. And to determine their long-term properties, we carry out what are called creep tests. And then we put the information combined with other reduction factors into a formula like this. This is typical US practice. We take into account creep, site damage, and environmental effects like chemical and oxidation. They're all going in there. And that gives us the allowable strength. I want to talk briefly about creep. A creep test looks like this, whereby we hang up a sample, we put a weight on the bottom, and we simply measure strain against time, and we leave it there for a long time. This gives us a very good idea about long-term performance of these materials. And then the data is plotted in this way, where we have the load applied versus the time, in this case, to rupture. And the relationship is that red line you can see there. And the time axis is logarithmic and it's in years. So I've put a dot there at around about 120 years, which is a typical design lifetime. And then that gives us the load we should apply to make sure that the rupture only occurs at that point in time. What happens at the shorter times? Well, we can't really measure that with creep testing. It would be a bit dangerous to arrange a creep test to fail in a few seconds. But we can look at this with tensile testing. And tensile testing, this is a typical test using the ISO standard, where the rate of elongation is 20% per minute. So this one finishes in about 30 seconds. So we can add that kind of information to the diagram like this, and that's where it would come. So if we call that a 100% of tensile strength, then that occurs at 30 seconds, and we get now a more complete relationship. But we can add another line here, which is called the residual strength. Now, what does that mean? Well, it means that as time goes on, the actual tensile strength in that geogrid is remaining the same. It's only when you approach the design life, you get this drop-off because it's a mode 3 behavior. How does it work then? Well, in our own creep laboratories, we have quite a few creep laboratories. For many years, every time we took down a creep test, even one after several years, we would check its tensile strength using the same procedure to measure the tensile strength before the test started. And then we compare the two. So here is a graph showing the retained tensile strength compared to the strain reached in the creep test. Now, what you can see for the majority of the data, it's around about 100%. This means you take down a specimen after, say, 5 years. It's been resting there with a high load on it, and you measure its tensile strength using a fast test, and that strength remains the same, and that's the residual strength. There are some points here which were close to rupture, and they had dropped down in terms of their tensile strength. What's affected more than that is the retained strain at failure. So we find that the strain of failure does reduce a bit, not surprisingly, because you stretch the geogrid. So what I can do, I can add that data, there, the black symbols for the 20 centigrade data to this diagram. And you can see how it's working now. And often people will look at that and say, okay, well, in that case, why don't we design for 100% tensile strength? Well, problem was, if you do that, it fails in 30 seconds. We need to set that particular long-term strength to make sure that that rupture occurs at the required design lifetime. If we were to do a tensile test which finished in 3 seconds, it would look something like that. That's quite difficult to do. So we would then have a different reference. If we followed the ASTM procedure, which is a slower test rate for tensile testing, it would be the green line. So one thing that's important to realize is that when you look at creep reduction factors, you need to be aware of the standard used to measure the tensile strength, because it can affect the creep reduction factor. Creep is absolute, but tensile strength depends on the procedure used to measure it. So just a little point to make from this. And here's back to that diagram of the 3 modes of behavior, 1, 2, and 3. Creep is mode 3. So here's an interesting point that, say, as we often do in research, we recover some polymer geogrid from, say, an old structure, 10 years old. We take out a piece, we dig it out of the soil, and we test it. And we might find a reduction in strength. So there we are, say, at 10 years. And that reduction in strength is going to come principally from the initial installation damage, combined maybe with chemical effects or exposure, if it's an exposed piece of geogrid, UV light, but not from creep, not to any significant extent, because creep is not degradation. And I hope that this little discussion gets that point across. But we still have to take into account long-term behavior in terms of a creep reduction factor. Now, just 2 points to go, and I think we'll be through in the next 10 minutes. But this is one which I've seen confusion over. Safety factors, wall design versus stability analysis. Let's have a look and see what I'm talking about. So let's take a very simple cross-section of a reinforced soil retaining wall. You can see there the layers of geogrid and so on. We're used to that cross-section. And I want to do a calculation for sliding on the base of the wall. And there would be the formulae I need. The driving force would take into account the earth pressure, and the resisting force would take into account the weight of the soil and the frictional resistance on the base. Well, let's just assume that the sliding interaction factor is 1 in this case. It doesn't really matter for what I'm doing. So let's take some typical values. I'll make it 5 meters high. I'll give it some properties. And then we'll do some calculations. We calculate that resistance, which comes to 52 times the length. And we calculate the driving force, which comes to 75. Of course, this is in kilonewtons per meter. And then having done that calculation, to get a safety factor of 1.5, we simply put R equals to 1.5 times S. And that gives us a length of 2.17 meters to get that required safety factor. So let's change it now. Let's make L 2.17 meters. So that length is giving us the required safety factor of 1.5 against sliding on the base. But what I'm now going to do, I'm going to reanalyze, but I'm going to set the soil strength value to a different, I won't call it phi, I'm going to call it theta now. And I'm then going to find a value that makes R equal to S without any safety factor on sliding. So I change, you can see down there inside the black circles, I'm going to change that to a thing called theta, like that. And I can then do my calculations again, because there is the equality I need to get the required safety factor. And if I put the numbers into that, I get this. I get a certain number times tan of phi equals a certain number times the Ka value. Of course, Ka includes phi. So the only way I could solve that was to make a spreadsheet and do it by trial and error. But to do that, I found that the phi should be 26.05 degrees. And then if I compare that to the original phi of 30, then the ratio of the tangents, which is how we normally would calculate a safety factor on soil shear strength, that ratio is 1.235. It's not 1.5, it's 1.235. And perhaps to make it even clearer, if I put that wall into a slope stability program, and I use, in this case, a non-circular technique, I find that my safety factor also, it's slightly different, 1.236. But this is a rather important thing to realize. Important conclusion that when we look at either a wall design method or stability analysis, then we get safety factors, or we use safety factors. So if we have a 1.5 from the wall analysis, then when we look at the method of slices, which is applied to the soil shear strength, and it's applied everywhere within the soil mass, not just on the base of the structure, then we get a different value. And in nearly all situations, F from the wall design method is going to be greater than F from the method of slices in stability analysis. Last thing, and I think we'll finish in the next 5 minutes. So, and this is something which is a bit of a passion for me, which is the approach to internal stability calculations. And I did actually use the similar slides in a Tensar webinar, not quite recently, but I think the audience today is largely different. So I hope you don't mind me using them again. So when it comes to internal stability, I like to start with what I call extreme cases. So if we have our block of reinforced soil without any reinforcement, and then the backfill behind it and the foundation soil, which we're used to that particular cross-section now, then if we have no reinforcement, and I ask you, what's the critical failure surface? Then if you can remember back to your earth pressure theory, you'll tell me almost certainly it's the Rankine wedge given by an angle of 45 plus 5 by 2, like that. And you'd be right. So let's go to another case. So I'm now going to fill up my reinforced soil structure with reinforcement, but I'm going to give it 0 strength. You might say that's a bit strange. However, it's just to make a point. So what is now the critical mechanism? It's going to be the same, because if it has no strength, then you're going to get that same Rankine critical surface. Right, now let's go to another extreme case, and let's give the reinforcement infinite strength. That means that the failure mechanism cannot touch it, because as soon as it touches it, it gets an infinite resistance. That means that the critical mechanism is going to be a surface going in between the lower 2 geogrids and coming up the back at the Rankine angle. That would be the critical mechanism. So let's now move away from these extreme cases and go to some, well, less extreme. We'll now look at finite strength reinforcement. And if we do that, then almost certainly our critical mechanism will be some form of 2-part wedge in between those 2 extremes we looked at just now, something like that. And what we will find, or if we do a bit of thinking about this, we'll realize that if you have relatively strong soil and weak reinforcement, you'll tend to get your 2-part wedge somewhere up there. And if you have relatively weak soil and strong reinforcement, it'll come down, because the surface where it goes through the geogrid wants to avoid the geogrid as much as possible. So it comes down to a lower angle. So you're going to have a variety of possible 2-part wedge mechanisms depending on the situation. One more extreme case is if I make the geogrid extremely long, but still finite strength, then the critical mechanism is going to come back to the Rankine wedge, like that. All right, nice in pictures. What about in reality? Is that what's going to happen? So I've looked at this using stability analysis, and I've used a very nice technique. I've used it already in this webinar, but I'm going to explain it slightly more detail now. But I've used a program called Tensar Slope, and I've used a very special non-circular search routine called a genetic algorithm, SGA for short. And the way this works is that we put into it a random surface, and then the program will refine it until it finds the lowest safety factor. And in the particular case I'm going to show you, the random surface is made of 15 little lines, which means that with 15 lines, you could end up with almost any shape. What I mean by that is, if there are 15 random lines like that, if that's our starting point, and we let the procedure refine this to find the critical surface, well, it could easily be a circle, or look like a circle, say like Bishop, or it could end up being a nice linear wedge, maybe, or it could even end up being some kind of exotic logarithmic spiral like that, which is a well-known mechanism often used in reinforced soil. So let's go into the software and let's see what happens. So here is a cross-section. It's, in this case, an 8-meter high structure, 5-meter long geogrid with a surcharge on the top. And in this case, I've set phi of 39 degrees, so quite a good fill. And the geogrid has a 28 kilonewton per meter long-term design strength. So I then open up my analysis window. I open up this genetic algorithm, which allows me to populate the cross-section with random surfaces like this. It's a very nice thing to watch, and it's remarkably clever. And having done that, we then run it, and we watch the program refining this down to find the lowest safety factor. And by this time here, I've got 110 generations now of the surface. And I find a safety factor of 1.3, just over 1.3 for that situation. A very typical target. So what I'm going to do now, oh, sorry, yeah, there's the final analysis. So you can see it is a really nice 2-part wedge that's been created. And this is now strong soil, weak geogrid. I'm now going to switch over to weak soil, strong geogrid. And if I simply analyze the same surface, which I have done there, the safety factor about 1.47, quite a lot higher. So what I shall now do, I shall go back to my algorithm. I'll repopulate with random surfaces and run it again. And I find as I do this, I see appearing in front of my eyes a 2-part wedge, but it's much lower down the structure now, like that. So that's the situation with weak soil, strong geogrid. Safety factor also just over 1.3, similar to the previous one, but a different arrangement of soil strength and geogrid strength. If I now make the geogrid very long, was my last case, if you remember, and analyze that, we get a safety factor of well over 2. So if I now run the algorithm again, what do I find? It reduces down to a straight line, which is essentially the Rankine wedge. Safety factor just over 2. So, conclusion from this last number 11 point is that if you use tie-back wedge methods, which are used in many codes and standards, they rely on a single internal mechanism when they look at the internal stability, typically the Rankine or Coulomb wedge. And everything is based around that one mechanism. What I've just shown to you, that's not necessarily going to be critical. So in the 2-part wedge approach, we don't do that. We look at very many different combinations of 2-part wedges. We look at them from the base and at different levels up the structure to find the best design. And this offers many advantages, which I haven't got time to talk about today. That would be going into the second series of 11 points. But this offers many advantages over the tie-back wedge method. So I've come to an end. We've covered these 11 points. I hope if you've managed to stay with me right through this, that you've found some things there maybe a bit different, things that you hadn't seen before. But I hope it's clarified a number of points and issues when it comes to the design of reinforced soil structures. So thank you very much. Just to remind you that in October, it'll be a kind of extension of the topic today, where we'll look at a specific reinforced soil structure type, which is load-bearing bridge abutments supported on polymer geogrid reinforced fill. Thank you very much.
Terima kasih kepada Bapak Michael Doby atas paparan menariknya. Sambil memberikan waktu kepada Pak Michael Doby untuk membaca pertanyaan yang sudah masuk, sekaligus menunggu pertanyaan lain, saya ingatkan kembali kepada Anda yang memiliki pertanyaan dapat bisa langsung disampaikan melalui fitur Q&A yang terletak di bawah layar Anda. Pertanyaan dipersilahkan untuk disampaikan dalam bahasa Inggris. Kami mengajak Bapak, Ibu, dan teman-teman yang hadir di sini untuk mengikuti berita dan informasi terkini seputar PT Multibangun Rekatama Patria dan MRP Webinar Series yang akan datang di bulan depan dengan follow dan like media sosial kami. Follow Instagram kami di @multibangunrekatama-patria, Twitter kami di @multibangunnrp, Facebook dan LinkedIn kami dengan nama PT Multibangun Rekatama Patria, dan kami juga hadir di TikTok dalam username @multibangunpatria. Baiklah Pak Mike, apakah sudah siap?
Okay, Kiki, terima kasih. So I have some questions here. They're quite long, so I've been reading through these. The first one, what can we do after preparing the reinforced soil structure if we build concrete wall, but we forget to calculate extreme condition? I to do with, say, with rainfall. We do know there is a slope coefficient factor and safety factor. In other words, we've got to achieve a certain safety factor, but those include on facing the extreme condition to prevent concrete walls. Okay, this seems to be a question about what happens if you have a design, in particular, of a concrete structure which is inadequate. When you look into the actual conditions, that's an interesting question. I mean, if you've got everything wrong, probably you need to demolish it and build it again. But one quite nice technique we can use with reinforced soil in the case of existing concrete structures. So say you have a gravity concrete retaining wall, or even a cantilever one, and it turns out for some reason it's inadequate, or you want to increase loading or something like that, then one way of dealing with that is to actually build a reinforced soil structure behind it and leave a space so that there is no you don't get any earth pressure applied to the back of the concrete structure. I'm not sure that's exactly answering the question, but it's one way we can use reinforced soil techniques to deal with situations where perhaps we don't have an adequate existing design. We tend to call them thrust relief structures, and they're quite common. For example, in many cases where we have old historic structures, especially, say, for example, in ports and harbors, we have old quay walls and people want to increase loading from, say, gantry cranes. Then one way that that's been done is to build a reinforced soil structure behind the existing wall without demolishing it. So it is something that can be done. Now from Abraham, in more depth, the layers automatically need more design specifically for interaction between film reinforcement. Can you tell some minimum depth for using reinforcement soil structure due to minimum prices? Well, I think this is to do with the economy of structures. Generally, with reinforced soil design, one of our targets is to optimize in terms of the cost. So that's really what we're trying to do. So in design methods we use, it's our normal main target. Clearly, we want to keep the cost as low as possible at the same time providing the adequate safety factor. And some of the techniques we use, like the two-part wedge approach, where we have automatic routines to do this and help us do it, are extremely effective. That's a whole big topic by itself. And I didn't go into the details of design procedures today. I talked about the principles a little bit, but I think that's our target. Safe structures, but to keep them economically viable. Gives me permission to ask, I've seen on your YouTube there is an incident on the road and the road suddenly collapses. What is the cause? Does the mixture of ingredients, I'm not quite sure which image that is, but I know I have been showing some of these. There are a couple of cases of facings collapsing from retaining walls in Indonesia. And I sometimes show people those pictures because rather like the picture I showed in the UAE, that was the loss of the facing. In the case of the UAE, it was because of undermining due to erosion from a stream. In other cases, it could be for other reasons. But when we look at design, we have to look at all of it. It includes the reinforcement, the fill, which is the main component, but also all of the extra pieces like the facing. So we pay special attention to connection between facing and reinforcement. Now, there was a webinar a little while ago organized by the Australian chapter of IGS, where I did speak about the issue of designing for the connection strength. And I think that's probably one of the problems in those particular images, which I occasionally do show to people. How effective percentage of the length of the anchor to resist the soil shear to the height of the retaining wall? Oh yeah, I think we're talking about here the requirements of the ratio of L, length of reinforcement, to H, the height of the structure. In most codes of practice, it's recommended you should be using a value of 0.7. However, that's not always given as an absolute requirement. Many codes of practice say you should use 0.7 for your initial assessment, but if you have particularly good conditions, a good foundation, high quality fill, then you may reduce that. In fact, in our own design recommendations, we would sometimes go down to 0.6, but we don't like to go much less than that. However, if you're moving into areas of, say, designing with clay fills, designing for earthquakes, designing with higher water pressures, then the L over H, that ratio is going to become probably higher than 0.7. And we would find, say, with typical clay fills, we might be approaching a ratio nearer to 1, 0.8, 0.9, something like that. There is no fixed answer, but also with strong earthquakes, which is something I'll talk about in the 10th of these webinars, in strong earthquakes, then that tends to result in you needing a larger block of reinforced soil. And if the block of reinforced soil is larger, then the geogrid must be longer. So L over H must be greater. So there isn't one answer, but it's something that comes out of the design. But 0.7 is a good target. In experience, how many years can anchored polymers survive against material weathering? This is a wonderful question about durability. Well, I guess in terms of actual real installations in the real world at the moment, polymer reinforced structures, the oldest ones now would be, let me think, approaching 50 years, certainly 45, probably the very earlier ones. So we are beginning to get some real long-term information. And we do find that on the whole, if a polymer reinforcement has been properly formulated using the right protection. So for example, in terms of oxidation, we use antioxidants. In terms of hydrolysis of polyester, we need to make sure we have, for example, high molecular weight, and we need to avoid certain extreme pHs. If we have followed those conditions, then the target lifetime of, say, 100 years or 120 years we typically use for highway structures is easily achievable. We haven't proved it yet, but the target of what I call the lifetime prediction testing is to try to give us a very good indication of what might actually happen over these very long time periods. One nice example, one of the longest exposed structures that has been examined was one built on the west coast of the US. It was a wraparound structure, so the geogrid was kind of exposed to the elements. It was exposed to rain and sun and so forth for almost 40 years. And they removed some samples from that. And just based on simple testing, the geogrid was unaffected. There is a paper. The main author is the younger Leszczynski, not Dov Leszczynski, but it's his son who did that work on that particular investigation. Very interesting. Very nice one to look about. So Mr. Bahri, how to handle an incident in a project where a landslide occurs due to water scouring? Wow, yeah. Is it effective to use bamboo saplings? Well, it depends how this is, what's going on here. I mean, if you have a landslide essentially going through the foundation of a structure, then you're going to have to demolish it and start again. Can you actually improve it by, say, using ground anchors. Maybe it's possible. It tends to be very expensive. But once you have a landslide occurring, especially in clay soils, the problem is it puts a plane of weakness into the soil. And once the plane of weakness is there, then it's not a good idea to keep that either within or underneath your structure. So it's best to remove it, which can only be done by excavation. If you do decide to try to rebuild above a landslide, then you need to be very careful to measure the actual soil shear strength, we call it the residual soil shear strength of the materials in question. And if they're clays, then residual shear strength can be very low. It can be 8, 9, 10 degrees, depending on the nature of the clay. So each situation is going to have its own solution. But one thing I always like to tell anybody who's looking at the repair of a failure is to make sure you understand the mechanism of failure before you try to repair it. You often hear of cases where people have a failure, they rebuild it, next rainy season it fails again because the issue wasn't resolved. That happened with a very famous case in Hong Kong of a reinforced soil structure where that had a problem with rainfall, and it happened twice. So understanding the problem and dealing with it and finding a solution really extremely important. Now, at Noro, for the reinforced soil blocks, since it's usually located at the roadside, then many utilities, cables, lighting poles, drainage would interfere with the geogrids. This is a very, very good point. Yes, it is correct. So if you have your reinforced soil structure and you have a road on top, you may have trenches dug through it for services. You may have lighting poles. You may have crash barrier poles, all sorts of things. Basically, we need to design for that. So if you're making holes in the geogrid for, say, lighting posts or for crash barriers, then what we normally do, we take a reduced area of the geogrid in our calculations, because we can do that, but we need to be aware of it. If you're dealing with a trench, of course, that's continuous. It goes all the way down through the geogrid. So we quite often have to look at that and design specifically for the case of the trench. If you have a very, very deep trench just behind a facing, then probably what you need to do is to design a reinforced soil structure behind the trench to stabilize the soil at that location, and then put the services in front of it with a further structure in front of that. So these things are problems. They should all be designed for very carefully and taken into account at the beginning. Of course, the worst thing to happen is that you build your reinforced soil structure, and then the electricity board or the water board comes along and say, we got to put a 2-meter trench right the way through that. And then that can be more of a problem. And we'd have to think very carefully in that situation. But I see a comment here from a very dear friend way over on the west coast of the US, from Gary Sander. Gary, thanks for listening in at this time. But he's reminded me that it's Ben Leshinsky. I'd forgotten his name. You're absolutely right, Gary. Thank you for that. Ben Leshinsky, who did the investigation into that structure in Oregon in the US. A really wonderful piece of work to demonstrate the long-term performance of these materials. So sorry, just a slight dry throat. I think that tells me I'm coming towards the end of this. Sorry. Right, finish off. Can you suggest user-friendly FOS calculation software for the beginner? I understand that most of it needs a license. Yes, that's the case. Are there any freebies? Probably there are some. So sorry. My throat has become very dry at the end there, not because of the question, Jonah, but I'd have to say that there probably are some free or online bits of software which can be made use of for doing stability analysis. I'm not very familiar with them. Most of the better ones you do need to buy a license. There are some which are much more user-friendly than others. Of course, you have to build up a model, which requires you building the geometry into the software and then analyzing it. I would suggest that it's best to get some help and advice on that more directly. You can certainly, for example, you can talk to PT Multibangun, who can help you with that. If you want to do it yourself, then again, talk to us, and there are ways we can deal with that. There are certainly lots of free bits of software around to do reinforced soil retaining wall design. Some of them are produced by manufacturers like ourselves. Some of them are produced by other authorities, but they don't necessarily, for example, do the method of slices for you. They'll use what we call the retaining wall design methods, and they're slightly different. And a last question here. Some more water's arrived. Thank you very much, Sandy, for doing that. Permission to ask, maybe it is funny, but can you explain how to do maintenance of a reinforced soil structure? That is a good question. Very good. What about maintenance? Well, as a general rule, the majority or most parts of a reinforced soil structure don't really need maintenance, but there are certain things that would do. So, for example, we normally build various kinds of drainage measure, either for surface water drains or for internal drainage, and those can need maintenance. If you just build a drain and leave it and expect it to work properly for 120 years, you're going to be wrong. So keeping drainage working properly is probably one of the main areas for maintenance. Another one is if you've built, say, a lower angle structure and you finish it with vegetation, well, you need sort of gardening maintenance then. You would like to make sure that your vegetation stays nice and healthy, especially if you have a distinct dry season and wet season like we have here and in many parts of the world. Then yes, there is maintenance required then. One interesting area, just perhaps I'd mention there, could be fire damage. In some situations, if you have vegetation which gets very dry, then maybe in the dry season, if you have a bit of bad luck, you might have a grass fire, say, going across there. And if you've only got the geogrid on the facing, then you might damage it. Generally, it won't burn inside the soil. It can't do that. There's no oxygen. But of course, it can melt or be burned away on the facing. That can be repaired. But if there is a big risk of surface fire, it's best to use some kind of steel mesh system. And you might say, well, steel mesh is going to have a problem with corrosion. Oh, you've got to protect it from that. So that is all part. So then it becomes relatively maintenance free. So yes, it's a very good question about maintenance. A well-designed reinforced soil structure shouldn't need much in terms of the reinforced soil block itself, but it's the bits around the edges. Yes, maintenance, some kind of maintenance program would be a good idea for this form of structure. Well, that seems to have come to the end of the questions. I hope for everybody I've provided an adequate answer. I don't think anything else has arrived since I started. I don't think so. So I shall come to finish. Thank you very much again, everybody who's listened in today. And I'm going to hand back now to Kiki, who will take us to the next part of this event. Thanks very much.
Pak Mike, terima kasih sekali lagi atas waktu, paparan, dan jawaban yang diberikan. Bapak, Ibu, dan rekan-rekan sekalian, kita akan beralih ke sesi selanjutnya, yaitu kuis berhadiah. Kuis berhadiah ini akan dipandu oleh Bapak Tri. Kepada Bapak Tri, dipersilahkan.
Oke, terima kasih buat Ibu Kiki atas waktunya. Selamat siang Bapak Ibu sekalian, perkenalkan nama saya Tri yang akan memandu acara games kali ini. Bapak Ibu jangan pergi dulu ya, jangan ngantuk, melek dulu lihat soalnya tuh nanti ya. Games kali ini berhadiah total Rp450.000 untuk 3 orang pemenang. Pemenang pertama mendapatkan Rp200.000, pemenang kedua mendapat Rp150.000, pemenang ketiga mendapat Rp100.000. Lumayan buat uang jajan Bapak Ibu nih, siang buat makan siang lumayan. Untuk mengikuti games kali ini, Bapak Ibu cukup membuka browser Bapak Ibu dan masuk ke menti.com. menti.com ya Bapak Ibu, buka browser baik di smartphone maupun PC, lalu ketikkan menti.com, menti.com ya. Oke. Ayo Bapak Ibu masuk ke menti.com. Nah, setelah masukkan kode yang ada di layar Bapak Ibu yaitu 71231655. Masuk ke menti.com, menti.com, lalu masukkan kodenya 71231655. Nah, setelah masukkan kode, isikan nama Bapak Ibu sesuai dengan nama yang diregistrasikan di webinar kali ini ya Bapak Ibu ya. Harus sama namanya supaya nanti kalau Bapak Ibu menang, panitia gampang menghubungi. Untuk memenangkan games kali ini, Bapak Ibu cukup menjawab dengan cepat dan benar. Jadi benar aja nggak cukup ya Bapak Ibu, harus cepat, benar. Jawabannya pilihan berganda. Pertanyaan berhubungan dengan paparan yang sudah Bapak Mike tadi berikan ya. 3 pertanyaan jawabannya pilihan berganda, harus cepat dan benar. Sambil menunggu yang lain, kita tunggu yang lain masuk ke menti.com, lalu masukkan kodenya dan isi namanya. Oke, tunggu dulu. Yang lain masuk, ayo jangan tolak rezeki Bapak Ibu. Ini hadiah nih, aduh, uang makan nih disia-siakan nih. Yang ngantuk bisa beli kopi. Yang lapar bisa pesan makanan. Di warteg lumayan Bapak Ibu, bisa berapa bungkus itu. Bisa traktir teman-teman tuh. Kopi bisa 10 gelas kali. Bisa nggak tidur-tidur. Ayo Bapak Ibu masuk menti.com, masukkan kodenya, isikan nama Bapak Ibu sesuai dengan nama yang diregistrasikan di awal ya. Waktu daftar webinar ini ya. Ayo yang lain masuk dulu. Jangan pergi dulu. Tolak rezeki, aduh. Lumayan ini. 200.000, 150, 100.000. 100.000 kopi bisa 10 gelas tuh Bu di warteg Bapak Ibu. Ayo kita mulai ya Bapak Ibu ya. Jawab cepat dan benar. Pertanyaan pertama. Lihat di layar, jawab cepat dan benar ya. A soil report provides the following soil parameters for a possible RSS fill material. Which would you use for design? Ayo tuh. Pertama, SU equals 120 kilopascal. Kedua, C equals 35 kilopascal. Phi equals 10 degree. Yang ketiga, C dash equals 2 kilopascal. Phi dash equals 29 degree. Ayo Bapak Ibu, pertama, kedua, ketiga, cepat dan benar. 30 detik lagi Bapak Ibu. Pertama, kedua, ketiga, cepat. Yang nyimak nih bisa jawab pasti. Gampang nih Bapak Ibu. Yang nggak nyimak jurus touchscreen aja langsung Bapak Ibu. ABC 1, 2, 3 cepat. Mau dapat hadiah harus cepat. Cepat sama benar Bapak Ibu ya. Benar tapi lama nggak bakal dapat. 3, 2, 1. Ayo waktu habis. Nah jawaban yang benar adalah yang ketiga ya Bapak Ibu ya. C dash equals 2 kilopascal, phi dash equals 29 degree ya. Nah, poin tertinggi kali ini diraih oleh ayo, siapa ini? Kita lihat. Nah, ini nyimak nih pasti nih poin tertinggi nih. Enggak jurus touchscreen nih ya. Harus nih, lihat nih. Siapa yang tertinggi nih? Ya, tertinggi Ibu Nina Y. Ibu Nina. Wah, pertahankan Bu, ayo. Lanjut pertanyaan kedua ya, Bapak Ibu. Jawab cepat dan benar. Cepat benar. Harus cepat sama benar. Ayo. Mau dapat hadiah kan nih? RSW design calculation give Fs equal 1.5 for sliding on the wall base. When you check this using the method of slice, do you expect Fs to be? Pertama higher, kedua lower, ketiga the same. Ayo Bapak Ibu, cepat. Pencet Bapak Ibu. Touch screen. Aduh, kayak warteg aja Bu. Nih, ini gitu langsung nyimak, cepat. Higher, lower, the same, Bapak Ibu. Ayo. Lumayan ya, aduh, buat makan Bapak Ibu. Aduh. Makan siang Bapak Ibu, jangan ngantuk dulu, udah langsung. 24 detik lagi. 21, 20, ayo. Aduh, udah lama ini yang lain udah, aduh, kalau jawab udah detik-detik ini nih, aduh. Lewat Bapak Ibu dah, melayang dah poinnya. Higher, lower, the same. Ayo, yang nyimak mah udah set, merem udah dapat Bapak Ibu. Ya, waktu habis. Jawabannya adalah lower. Dan poin yang memimpin saat ini adalah, ayo siapa? Ayo. Ya, Ibu Nina Y lagi. Ayo, Ibu Nina Y. Ayo, pertahankan. Bapak Ibu, lanjut pertanyaan ketiga. Yang lain jangan mau kalah ya. Cepat dan benar. Cuman 3 orang. You recover some geosynthetic reinforcement from a 10-year-old RS structure. There is a reduction in tensile strength. Is this likely to be due to? Yang pertama, installation damage and chemical degradation. Kedua, installation damage and creep. Ketiga, chemical degradation and creep. Ayo Bapak Ibu, cepetan. 1, 2, 3. Juara keempat, kelima nggak dapat Bapak Ibu. Tapi saya tetap kasih ucapan terima kasih doang. Dapat sertifikat Bapak Ibu. Cuman 3 orang doang ya Bapak Ibu. Yang keempat, kelima, karena seterusnya dapat sertifikat. Tenang aja. 20 detik lagi. 19. Harus cepat Bapak Ibu. Aduh. Kalau nyimak nih tadi nih, merem aja udah bisa jawab. 7, 5, ya 3, 2, 1, habis time out Bapak Ibu. Jawaban pertama, jawabannya adalah, nah tuh, yang pertama, installation damage and chemical degradation. Nah, pemenangnya adalah, kita lihat nih ya, pemenangnya, ayo. Weh, Bapak Zakaria dengan poin 2959 poin. Dan kedua, siapa nih? Mikrofa Hanifah, ketiga Antoni Gunawan. Wah, Bapak Antoni udah langganan ini ah. Selamat untuk para pemenang, silakan klaim ke panitia hadiahnya ya. Waktu saya kembalikan ke Ibu Kiki. Ya, silakan Ibu Kiki.
Baiklah, terima kasih kepada Bapak Tri yang sudah memandu acara games berhadiah pada pagi hari ini, dan selamat kepada pemenang. Dengan berakhirnya games tadi, maka sudah sampailah kita di penghujung acara. Kami mengajak Anda untuk mengikuti MRP Webinar Series selanjutnya pada 27 Oktober 2021 pukul 10 waktu Indonesia bagian Barat dengan tema Load Bearing Bridge Abutment Supported on Polymer Geogrid Reform Fields. Anda dapat langsung mendaftarkan diri di link bit.ly/webinar MRP9. Untuk informasi mengenai sertifikat dapat diakses melalui link bit.ly/mrpweb8 yang juga tertera pada kolom chat atau yang tertera pada layar Anda. Apabila Anda memiliki pertanyaan atau terdapat kesalahan penulisan nama pada sertifikat Anda, silakan hubungi Rifa melalui WhatsApp di 0822 9851 0700. Untuk informasi lebih lanjut terkait PT Multibangun Rekatama Patria dan acara-acara kami selanjutnya, silakan ikuti media sosial kami. Akhir kata, kami mengucapkan terima kasih kepada seluruh peserta, pembicara, panitia yang terlibat dalam acara ini. Kami juga memohon maaf jika terdapat kesalahan dan perbuatan selama acara berlangsung. Kami menunggu Anda di MRP Webinar Series selanjutnya di bulan depan. Sampai jumpa dan selamat siang.
Can't be right, yeah. I do the same thing. I told you that I never would. I told you I changed, even when I knew I never could. Know that I can't find nobody else as good as you. I need you to stay, need you to stay. I do the same thing. I told you that I never would. I told you I changed, even when I knew I never could. Know that smooth like butter, like a criminal undercover. Don't pop like trouble breaking into your heart like that. Cool shade stunner, yeah, owe it all to my mother. Hot like summer, yeah, I'm making you sweat like that. Break it down. Ooh, when I look in the mirror, I don't know too hard to do. I got the superstar glow, so a side step I like to make. I like when you move back with me, baby. You know that I got that heat. Let me show you 'cause God can see it. Side step right left to my beat. Smooth like butter, pour you in like no other. Don't need no usher to remind me you got it bad. Ain't no other that could sweep you up. Listen to me now.
Hari ini aku dan temanku mau pergi ke gudang PT Multibangun Rekatama Patria. Kita jalan dari kantor yang di Jakarta menuju Bitung, Tangerang. Gudang PT Multibangun Rekatama Patria cuma 5 menit dari gerbang tol Bitung, Tangerang. Mari kita coba lihat. Wow, luas banget dan semuanya tersusun rapi. Cek website kami ya untuk lebih lengkapnya. Tahu nggak sih apa itu dinding penahan tanah atau retaining wall? Dinding penahan tanah atau retaining wall adalah struktur bangunan penahan timbunan tanah. Begini nih contohnya. Ada yang terbuat dari batu kali, terbuat dari beton dicor, terbuat dari beton dipancang, dan yang ini dari multi-block. Multi-block retaining wall system adalah dinding penahan tanah yang merupakan kombinasi dari blok beton dan tensar RE geogrid. Begini nih gambarnya. Di bagian dalam multi-block retaining wall system ada tensar RE geogrid. Yang ini nih, yang fungsinya untuk menahan tanah. Di depannya ada blok beton. Ini nih. Fungsinya sebagai penutup muka dinding. Gimana? Udah ngerti kan?
Can't be right, yeah. I do the same thing. I told you that I never would. I told you I changed, even when I knew I never could. Know that I can't find nobody else as good as you. I need you to stay, need you to stay. I do the same thing. I told you that I never would. I told you I changed.
Multibangun, kali ini kita akan bahas jenis-jenis alat berat yang digunakan di proyek. Yang pertama namanya ekskavator atau disebut juga backhoe. Fungsinya untuk menggali dan memindahkan material seperti tanah dan batu. Yang ini nih namanya dozer. Fungsinya untuk mendorong material tanah ke depan atau ke samping. Hal yang ini nih namanya kompaktor. Fungsinya untuk memadatkan tanah atau timbunan. Nah, yang ini nih namanya dump truck. Fungsinya untuk mengangkut dan memindahkan material seperti tanah, batu, besi, dan lain sebagainya. Yang ini namanya grader. Fungsinya untuk meratakan tanah atau material. Gimana? Sekarang udah paham kan jenis-jenis alat berat yang dipakai di proyek? Sampai jumpa! Halo Sobat Multibangun, kali ini kita akan bahas macam-macam jembatan. Yang pertama adalah jembatan girder atau balok beton atau beam bridge. Adalah jembatan terbuat dari girder atau balok prategang. Contohnya adalah jembatan tol Cipularang, Jakarta Bandung. Yang kedua adalah jembatan rangka baja yaitu truss bridge. Adalah jembatan yang terbuat dari rangka baja. Contohnya adalah jembatan Sungai Serayu yang ada di Jawa Tengah. Yang ketiga adalah jembatan lengkung atau arch bridge, yaitu jembatan dengan struktur utama yang berbentuk lengkung atau busur. Contohnya adalah jembatan Yotefa yang ada di Papua. Yang keempat adalah jembatan kabel yaitu cable stay, yaitu jembatan yang ditopang oleh kabel dan dikaitkan pada tiang utama. Contohnya jembatan Suramadu. Yang kelima adalah jembatan suspensi, contohnya jembatan Sungai Barito. Sampai jumpa lagi, bye!
Ela veio pro baile de shortinho pra exibir o bom baile de shortinho pra exibir o
Halo Sobat Multibangun, di video kali ini kita akan bahas step by step pemasangan multi-block retaining wall system. Yang pertama, kita lakukan pembersihan lahan atau land clearing. Yang kedua, dilakukan pemadatan lahan atau tanah dasar. Selanjutnya, pembuatan leveling pad atau lantai kerja. Selanjutnya, kita lakukan pemasangan blok beton yang pertama. Setelah itu, pemasangan lapisan pertama tensar RE Geogrid dan konektornya. Yang ini penggelaran tensar RE Geogrid. Kemudian, pemasangan batu pecah dan geotekstil sebagai drainase vertikal. Nah, semua tahapan tadi diulang terus hingga mendapatkan ketinggian yang diinginkan. Nah, jadi deh multi-block retaining wall systemnya. Gimana? Udah paham kan cara pemasangan multi-block retaining wall system? Sampai jumpa di video selanjutnya.
Sobat Multibangun, pada video kali ini kita akan bahas jenis-jenis fondasi pada konstruksi teknik sipil. Secara garis besar ada dua jenis fondasi, yaitu fondasi dangkal dan fondasi dalam. Fondasi dangkal adalah fondasi yang kedalamannya maksimal 3 meter. Sedangkan fondasi dalam yaitu fondasi yang kedalamannya lebih dari 3 meter. Contoh fondasi dangkal yaitu fondasi pasangan batu kali. Biasanya digunakan untuk bangunan rumah satu lantai. Contoh yang kedua yaitu fondasi tapak. Biasanya digunakan untuk bangunan rumah 2 lantai. Untuk fondasi dalam contohnya yaitu fondasi tiang pancang atau paku bumi. Contoh yang kedua yaitu fondasi bor atau bor pile. Kedua fondasi ini digunakan untuk fondasi gedung bertingkat dan jembatan. Bagaimana? Udah tahu kan jenis-jenis fondasi yang digunakan dalam bangunan teknik sipil? Jangan lupa follow dan like ya. Sampai jumpa.
This speech is my recital. I think it's very vital to rock around. That's right, on time. It's tricky. Here we go. It's tricky to rock around. That's right, on time. It's tricky.
Sobat Multibangun, di video kali ini kita akan bahas jenis-jenis geosintetik. Persatu, geosintetik adalah bahan tiruan atau sintetik yang digunakan dalam proyek konstruksi yang berhubungan dengan tanah atau batuan. Di video kali ini akan kita bahas adalah geogrid dan geotekstil. Geogrid adalah bahan geosintetik yang berupa lembaran dan memiliki bukaan. Ada triaksial dan uniaksial. Geogrid triaksial adalah bahan geosintetik yang memiliki bukaan berbentuk segitiga yang seperti ini. Fungsinya sebagai stabilisasi tanah dasar yang lunak pada proyek jalan dan area penumpukan. Geogrid uniaksial adalah bahan geosintetik yang memiliki bukaan memanjang satu arah yang seperti ini. Fungsinya adalah untuk perkuatan timbunan tanah atau lereng. Selanjutnya geotekstil. Geotekstil adalah bahan geosintetik berpori yang memiliki sifat tembus air. Ada woven dan non-woven. Pembahasan selanjutnya tunggu di part 2 ya. Sampai jumpa.
Menurut kalian, bikin jalanan di tanah lunak itu gampang? Main asal timbun aja. Gini efeknya kalau asal bikin aja. Nah kan, susah dilalui. Selain itu, rugi waktu sama rugi biaya karena sering memperbaiki. Seharusnya pakai geogrid Tri-X dari Tensar. Pemasangannya gampang kok, tinggal gelar, ditimbun, terus dipadetin, langsung deh bisa dilalui. Makanya pakai Tensar geogrid Tri-X untuk proyek-proyekmu.
Halo Sobat Multibangun, di video kali ini kita akan membahas alat pelindung diri yang ada di proyek. Yang pertama, helm proyek. Kayak video yang kemarin, jangan lupa dicek ya. Fungsinya untuk melindungi kepala kita dari benda yang jatuh dari atas. Walaupun AC ini jangan digunakan untuk naik motor ya, karena itu nggak aman. Yang kedua, safety shoes. Fungsinya sebagai pengaman pada tempat berlumpur atau becek. Juga mencegah kecelakaan fatal pada kaki. Selanjutnya, rompi proyek. Ia memiliki material retroreflektif agar mudah terlihat di lokasi proyek, terutama di malam hari. Berikutnya, sarung tangan. Fungsinya untuk melindungi tangan dari kecelakaan kerja seperti terpotong, tertusuk, dan terjepit. Selanjutnya, kacamata safety. Fungsinya melindungi mata dari debu dan partikel-partikel kecil yang berbahaya. Dan yang terakhir, body harness, biar tidak terjatuh. Nah, jangan lupa pakai APD ya.
Bang bang.
Halo Sobat Multibangun, kali ini kita akan bahas konstruksi bangunan termegah di Indonesia. Yang pertama, segmental retaining wall system terpanjang di Indonesia. Multi-box retaining wall system pada jalur kereta api Batu Ceper Tangerang ke Bandara Soekarno-Hatta. Konstruksi ini memiliki panjang 2,4 km. Yang kedua, jembatan terpanjang di Indonesia yaitu jembatan Suramadu, Surabaya Madura yang berada di Jawa Timur. Jembatan ini memiliki panjang 5,4 km. Yang ketiga adalah bendungan terluas, yaitu Bendungan Jatiluhur yang berada di Jawa Barat memiliki luas 8.300 hektar. Dan yang keempat adalah gedung tertinggi, yaitu Gedung Gama berada di Jakarta setinggi 310 meter. Dan yang terakhir adalah peninggalan sejarah termegah, yaitu Candi Borobudur. Candi ini memiliki luas 2.500 meter persegi dan tinggi 35 meter. Gimana? Menarik?
Halo Sobat Multibangun, di video kali ini kita akan bahas jenis-jenis geosintetik. Persatu, geosintetik adalah bahan tiruan atau sintetik yang digunakan dalam proyek konstruksi yang berhubungan dengan tanah atau batuan. Di video kali ini akan kita bahas adalah geogrid dan geotekstil. Geogrid adalah bahan geosintetik yang berupa lembaran dan memiliki bukaan. Ada triaksial dan uniaksial. Geogrid triaksial adalah bahan geosintetik yang memiliki bukaan berbentuk segitiga yang seperti ini. Fungsinya sebagai stabilisasi tanah dasar yang lunak pada proyek jalan dan area penumpukan. Geogrid uniaksial adalah bahan geosintetik yang memiliki bukaan memanjang satu arah yang seperti ini. Fungsinya adalah untuk perkuatan timbunan tanah atau lereng. Selanjutnya geotekstil. Geotekstil adalah bahan geosintetik berpori yang memiliki sifat tembus air. Ada woven dan non-woven. Pembahasan selanjutnya tunggu di part 2 ya. Sampai jumpa.
Halo Sobat Multibangun, video kali ini kita akan membahas perbedaan antara insinyur sipil dan insinyur arsitek. Insinyur sipil menghitung kekuatan bangunan. Insinyur arsitek mendesain keindahan bangunan. Insinyur sipil mendesain sarana dan prasarana seperti jalanan dan jembatan. Insinyur arsitek mendesain tata kota. Insinyur sipil harus mahir menghitung. Harus mahir seni menggambar. Insinyur sipil tidak harus paham warna. Insinyur arsitek harus paham warna.